In this podcast, we're going to look at Charles' Law and how it relates to the ideal gases that we've been talking about in class. The question we have to ask ourselves here is, how does volume relate to temperature? Charles explained, assuming that pressure remains constant, the volume and absolute temperature of a certain quantity of gas are directly proportional. We represent that mathematically through our equation. It's a proportion. And as with any proportion, as you increase one value, the other one also increases at the same rate. So how does this affect objects in everyday life? Let's say we have a balloon, and that it's at an average consistent temperature, and we know that temperature is the average molecular motion of the gas particles inside the balloon. If we were to double the temperature applied to that balloon, then we would know that the volume of that balloon would also have to double because of Charles's law. The volume of the gas is the size of its container because the molecules inside will move in a straight line until they impact something, either another molecule or the container. This requires lots of kinetic energy. So if you increase the kinetic energy in terms of heat, right, the size of the container is going to increase to accommodate the fast-moving particles. Something to note is that Charles' law must be used with the Kelvin unit of temperature measure. This is known as the absolute temperature scale, because at 0 Kelvin there is no kinetic energy, which is directly related to what we know about how particles move, as we've been seeing in lab. It is rather simple to find the temperature unit in Kelvin. Essentially, most of the problems you will see has the temperature in degrees Celsius. Since Celsius and Kelvin are the same size unit, all you must do is add 273.15 to Celsius to find degrees from Celsius to what it would be in Kelvin. Let's look at a sample problem from the textbook. Using Charles' law, what would be the resulting volume of a 2-liter balloon at 25 degrees Celsius that was placed in a container of ice water at 3 degrees Celsius? The first thing we must note is that our temperatures are not in Kelvin, so we must convert those. The initial temperature is 25 degrees Celsius because the balloon is not in ice water yet, and the final temperature is 3 degrees Celsius because the balloon is in ice water. We add 25 degrees Celsius plus 273 to convert it to Kelvin, and we get 298 Kelvin. For the final temperature, we add 273 to 3 degrees Celsius, and we end up with 276 Kelvin. We know our initial volume was 2 liters, so now the question is, what would be the final volume of the balloon if we were to cool it down? We apply our values to our equation, and we must solve for the final volume, so we must multiply both sides of the equation by 276 Kelvin. We can then cancel out 276 Kelvin on the right side of the equation, leaving us with 276 Kelvin times 2 liters divided by 298 Kelvin. Plug that into the calculator, and we find out that the final volume is equal to 1.9 liters. If we look at the math that we did, the Kelvin in the numerator is canceled out by the Kelvin in the denominator, leaving us with the units of liter for volume as our final solution. To do more practice with Charles' law, look for the math practice tutorial on the class website. Try your luck. This concludes this episode of the podcast.